Welcome to Chapter 7. This chapter is on experimental research, which we've been talking about, but specifically on independent group design. So let's go ahead and get started. Okay, so first we're going to review what an experiment is. And so I'm going to ask you a couple questions so you can kind of test yourself. So the first question is, in an experiment, what do we do to one of the variables that doesn't always happen accurately or at all in non-experimental research? And the answer to that question is we manipulate the independent variable in an experiment. And in non-experimental research, generally we don't always have the ability to manipulate the variable. Sometimes we do the research post facto or after the fact. Or sometimes the IV is manipulated naturally by the environment. So there's a bunch of different ways in which the independent variable cannot be manipulated by the researcher, but in that case you would have non-experimental research. And then the next question is, in an experiment, we can do what with our results that we can't do in non-experimental research? And the answer to that is determine cause and effect relationships. So remember, the goal of an experiment is to show that the independent variable causes a change in the dependent variable. So in order for an experiment to be a true experiment and not a quasi-experiment or some other form of non-experimental research, the independent variable must be under the control of the researcher. So experimental manipulation is the change that the experimenter deliberately produces in a situation, and the experimenter manipulates the variable that they think is causing the behavior while holding all other variables constant and unchanging. And this way we know that the variable we changed is responsible because it was the only thing that was different between the participants. And so the participants are assigned to groups by the researcher, and that is something that must occur in order for your study to be considered an experiment. And so we make sure that there are no systematic differences between the groups before the experiment. So an example of a systematic difference would be, let's say we wanted to measure aggression in 5th grade boys, and we didn't do random assignment, and we actually accidentally end up with everyone in the treatment group being from an inner city gang rehab program, and the control group being like a youth group. So this would definitely create some confounding variables. As a result of doing this random assignment to groups, we are able to conclude that any difference found after the treatment are a result of that treatment. And again, a big reason for that is because we control for all those extraneous variables. So true experiments are the foundation of scientific research and the preferred method of research because we can make those causal inferences. So also as review, steps in conducting an experiment. So the first step is to make a hypothesis. And a hypothesis is a statement about the expected relationships between your variables. The next step is to operationalize your hypothesis so that it is measurable. You put it in terms that are testable and measurable. And of course, you will need an independent variable and a dependent variable to do that. So step 3 is to consider what other variables besides the independent variable could affect the dependent variable, and then think of ways to control or eliminate them. In other words, limit alternative explanations for the variation so that you can be confident that the only thing affecting your DV is the IV, theoretically. Step 4 is to manipulate the IVs and measure the DVs. In other words, step 4 is to go ahead and carry out the experiment. So now that you have measured your dependent variable, you have a bunch of data. And so step 5 is to analyze the variation in the DV or multiple DVs if that's the case. So now that you have that data, you have to determine what statistical analysis you will use to analyze that variation. And then step 6 involves interpreting your results in terms of the effect that the IV had on the DV. And then it is in step 6 where you would make those causal inferences. So step 6 is all about drawing the inferences about the relationship between the IVs and DVs. And this is, of course, normally where we would publish our results as well. Okay, so we're going to talk now about where we do experiments. And so we can do experiments in the lab or in the field, and both of them can be done manipulating IVs, which means that you can have experiments in the lab and you can also have experiments in the field as long as you're manipulating that independent variable. So there's advantages and disadvantages to both. One of the main disadvantages that we kind of see all the time that we need to look out for in experimental research is what's called demand characteristics. So, demand characteristics can come from the experimenter or they can come from the situation itself that the participant finds themselves in. But demand characteristics are clues that lead participants to guess the nature of the study and then may change their behavior. So, we want to avoid those in any type of research. But the specific advantages of laboratory research are that you have high internal validity. That is the probability that any changes in the dependent variable are indeed a result of the manipulation of the independent variable. With lab research, you can have more control over the IV, you can have more control over secondary or extraneous variables, and you can more precisely measure your dependent variable when you have that much control. The disadvantages to lab research are that there's low external validity, that is, it's not necessarily generalizable to the real world. And part of the reason for that is another disadvantage, which is that it occurs in an artificial setting rather than the setting that your participants are normally in when they do the behavior you're observing. So some phenomenon can't be studied in a lab. It might not be practical. For example, if you wanted to study the brains of schizophrenics, it would not be practical to take an fMRI machine to 25 schizophrenics' house because it's like the size of an elephant. And it also, the problem with laboratory research is that sometimes you're looking to study a phenomenon where it would be unethical for you to do the manipulation. Like, for example, if you're interested in studying drug use, it would be unethical to give people drugs. In fact, depending on the drug, it could also be illegal. So, another disadvantage is that doing laboratory research is time consuming and costly. As you can imagine, to rent out the lab, any equipment that you may need, all of those costs are going to add up. And then the field experiments have advantages in that they actually have high external validity. So, generally, they generalize well to the real world. And what's good about field experiments is that they do occur in a natural setting. So generally, people are more likely to kind of behave as they usually would if they're in a setting that they're familiar with, comfortable with, like their home or their place of business. And then disadvantages of the field are that it can be low in internal validity. And the reason for that is you don't have a lot of control over the independent variables in field research. And so if you don't have control, you can't be certain of where the variance is coming from within your study. So then you would have the low internal validity. Another thing that leads to low internal validity is having less control over any extraneous variables, and then finally having less control over the dependent variable. So now we're going to look kind of more in depth at how we do experiments, specifically independent group designs, as opposed to dependent group designs, which we talk about in another lecture. But today we're focusing on independent groups. And so if we cannot make the initial assumption that our groups are as similar as possible at the outset of the study, in other words, if we cannot assume that our groups are equivalent before we expose them to the manipulation of the independent variable, then we can't make causal inferences after the treatment. So the question is, why is that? Why do we have to have equivalent groups to do an experiment? And the answer is that we have to be able to say that the only systematic difference between the groups is the independent variable. So in other words, we're going to test the hypothesis that violent TV causes aggression. So we get a bunch of 5-year-olds from the same daycare, and we split them into 2 groups. We make sure that none of them have come from homes with domestic violence, that none of them have high levels of testosterone, none of them are on bath salts. There is nothing chemically or anything altering their behavior to make them more aggressive. And we could even get people from different daycares in the same city, and then get people with similar IQs, similar socioeconomic status. We could do everything that is necessary to make sure that the people in our groups are as similar as possible, so that at the end of our study, if we do find an effect on our DV, we would know that, hey, these people are exactly the same. The only difference is half of them got the treatment and those half performed this way, and half of these kids did not get the treatment and they performed this way. So we would expect, obviously, in that situation, the kids that got the treatment to be more aggressive. And if they were, we'd say it's because of violent TV. We know that it's not because of domestic violence or any of these other things, because none of these kids come from homes with domestic violence. So because of that control, you're able to kind of make sure that your DV is being affected by your IV and nothing else. But all that is dependent on the assumption that your groups are in fact equivalent. So even though we know that there are individual differences, since most human traits do fall on that normal distribution, the curve, the groups should be pretty similar to each other on average with random sampling and random assignment. But how can we assume that our groups are equivalent at the start when we know that there are these participant characteristics, individual differences that we're grappling with as experimenters? So one of the things that we can do to make sure our groups are equivalent at the outset of our study is to randomly assign groups to independent groups, aka what we would call a between participants design in groups, or a between participant design in conditions of each level of an IV, for example. So if you wanted to study the effects of candy on hyperactivity, you could put people in the Snickers group, people in the Reese's group, and people in the sour gummies group, and see how that affects their behavior on some measure for hyperactivity. But what makes it independent is that if you're in the Snickers group, you cannot be in the Reese's group or the sour gummies group. So the people in the Snickers groups are completely independent of the people in the sour gummy group and the Reese's peanut butter cup group. And so it's important that those participants are randomly assigned to the conditions or the groups. So random assignment we've talked about before, but as a refresher, it's the process of assigning subjects or participants to the experimental or control groups randomly, so that each participant has an equal chance of being in either group. And so that gives us an equal chance that those participant characteristics will be comparable, that they'll be equivalent across the experimental groups or the conditions. And so you can do random assignment by just flipping a coin or drawing names from a hat, pulling straws. It doesn't matter how you go about it, as long as each individual participant has an equal chance of ending up in the experimental group as they do ending up in the control group. And so if we were to use the same participants in each group, so if we had the same people eat the Snickers and then we moved those same people to the Reese's peanut butter group and had them eat the Reese's, and then we moved them to the sour gummy group and had them eat the sour gummies, that would be a within participants design, because they're kind of serving as one group moving through these three levels of the independent variable, or moving through these three conditions of the independent variable. And so all we can look to analyze in terms of the variance with those people is going to be the variance within the group. So they're all going to all three conditions. So how did Sally's hyperactivity after eating Snickers compared to Dave's hyperactivity after eating Snickers? How did Sally's hyperactivity compared to Dave's after eating Reese's, and so on and so forth. So the within participants design looks to kind of measure the difference within people in one group. And then the between participants design is the one that we gave the example where there were different people in each group. So there were different people eating the Snickers, different people eating the Reese's, and different people eating the sour gummies. And then what we're doing is comparing the variance between those groups on hyperactivity. So who was more hyper, Reese's or Snickers? Snickers or gummy sours or Reese's, and every combination that you could do. So with independent or between participant designs, each score is independent of every other score. And that's one of the reasons it's called an independent groups design. So if we want to measure the effect of distraction, for example, like listening to the radio or not on workplace performance, if we wanted to look at that as a between groups design, what we could do is have one floor of an office have the radio banned, and then on another floor of the office, we let them carry on as usual, listening to the radio. And at the end of the week, at the end of the work week, we look to see which floor got the most work done, the group that got to listen to the radio or not. So we're comparing the difference between those groups, or the variance between those groups. If we wanted to do that same, if we wanted to test that same research question of what is the effect of distraction on workplace performance, we could also do a within groups design where we just look at one floor. So for a week, we would measure their work rate while the radio is there, and then after the week, we would take away the radio and measure the work rate again. So in that scenario, we're just comparing work performance within everyone on that same floor. Okay, so now we're going to look at some examples of completely randomized group designs. The simplest independent group design is where the researcher is interested in one independent variable with two or more levels. Research participants are randomly assigned to different levels or different conditions of one independent variable. So, for example, the independent variable of violent TV can have two levels. If one half of the group goes into the experimental group where they are shown violent TV, and the other half of participants is put in the control group where they receive a placebo, like watching Barney or something, or they just sit and do nothing for an hour. But anyways, we're going to now look at an example of a completely randomized group design with one independent variable and two levels. And then after that, we'll look at some more complex research designs. So as I said, one independent variable with two levels constitutes the simplest completely randomized independent groups design. And this generally is broken down into a control group and a treatment group. With this type of design, we can answer one research question, which is going to center around, did the manipulation of the independent variable affect the dependent variable? So let's look at an example of this research design. So let's pretend that the research question we're interested in is, would readers that believed the researcher had a biased interest, meaning that they held company stock, for example, in a study about herpes medicine, judge the study as less valid? So if the readers of some article in a journal, if the readers of that article believed that the person who did the research held company stock in the company that it did the research on, and let's say that that company is herpes medicine, would participants judge that study as less valid? So the way we could test this research question is randomly assign participants to conditions. In this example, we have one IV with two conditions. So 300 participants would all receive a research report on the impact of the herpes medicine that we're calling herp relief pain medication on people having a herpes outbreak. And so the two groups, the two conditions, or you can call them levels, the two levels of this are going to be randomly assigned participants, 150 of them, in level 1, and they would be told that the researcher did have stock in the company, so they had that biased interest. And then level 2, or group 2, condition 2, would be comprised of 150 participants that were told that the researcher had no biased interest. And so the variables here would be biased interest, or in other words, company stock, versus no biased interest. And the dependent variable would be participants in both levels rating the validity of the research report on several variables using a 5-point Likert scale, where 5 is very valid. So let's say the results are in level 1, the participants that got the biased interest, or were told that the person who wrote the article were biased, they held company stock, they rated the study as less valid than the participants in level 2. who basically were the control group and were not told that the researcher had biased interest. So the appropriate statistical analysis for this research example would be to do an independent t-test, and the reason for that is because you have two groups and you're testing the difference between them on their perception of validity. And so it's a hypothesis of difference that you're testing. You also would have interval data with your Likert scale. And so because of all of those factors, you would be able to do the independent t-test. So now we're going to look at a little bit more complex randomized group design that's independent. So if you had one IV with more than 2 levels, we could kind of visually represent that if you look on the slide with kind of this diagram here. So the IV, which we're naming A, has 3 levels. So level A1, level A2, and level A3. And those 3 levels or groups or conditions are where our participants are going to be in each one of those groups. And then with an independent groups design, we're going to compare the difference between the groups. So whatever our DV is, whatever we're scoring these people on, we're going to compare the scores we get in A1 with the scores in A2. We're going to compare the scores in A1 with A3, and then we're going to compare A2 and A3. So an example of this type of design could be if the researchers ask the question, does the way you study affect your performance on a test? So what you could do here is assign to multiple conditions. In this example, there's actually 4 different levels or conditions or groups. So you would randomly assign people to level 1, 2, 3, or 4. Level 1 is to read and copy as your strategy of studying. Level 2 is to read and highlight as your strategy of studying. Level 3 would be to read, highlight, and take notes. And level 4 would be to read, highlight, and generate questions. So the variables here are type of studying strategy, and then there's the 4 different types and the levels. And then the DV would be measured by the number of correct answers on a 20-item multiple choice exam. So again, because this is an independent group design, the participants in each group are completely independent of each other. They don't repeat groups. The people in level 1 read and copy, and then they go home and they're done. We never see them again. And the same for the rest of the participants. They don't move into another group or condition. So let's say the results are that the read, highlight, and generate questions group performed significantly better on the test than the read and highlight or read and copy. So that is an example of kind of analyzing the variance or the difference between the groups there. So then the appropriate statistical analysis for this research example would be a one-way analysis of variance or a one-way ANOVA. And one way means that you have one independent variable with multiple levels. If you had one independent variable with 2 levels, you would just do an independent t-test. So if you have a one-way ANOVA with if you have an experiment with 3 or more levels, then you would be doing a one-way ANOVA. And a one-way ANOVA also requires interval data, which we would have in this example because we're measuring the DV given a 20-item multiple choice exam. So we would just take the number of correct answers out of 20, and that would be our measurement of the DV. So we would take that DV and plug the values we get on it into our one-way ANOVA calculation. And as a result of that, we would be able to see if there is a significant difference between any pairwise comparison or combination of 2 groups. Okay, so the last randomized group design we're going to talk about is actually going to be called a randomized factorial group design because there's going to be more than one independent variable or more than one factor affecting the DV. So multiple factors is referred to as factorial, or in this case, a randomized factorial independent groups design. So there's probably many reasons why humans behave the way that they do. So designs that involve more than one independent variable are probably most kind of indicative of the real world and therefore have the highest external validity generally. So they allow us to assess the effects of each independent variable on a DV. In statistical analysis, these are called main effects. So how did Snickers affect how did type of candy affect hyperactivity, and then you could also add in another variable of like sleep. How much sleep did the person get? So you have one variable of type of candy on hyperactivity, and then you have the other factor or variable of sleep. So how did those two things affect the DV individually and together? So when we look at how each of those independent variables affect the DV, these are called the main effects. So how the groups and the candy conditions affect the DV, there's a main effect for candy. And then we look at the way the groups sleep scores affect DV, and so then we talk about the main effect of sleep on hyperactivity. And then the randomized factorial group design also allows us to look at what we call an interaction effect, which is those two variables, so sleep and candy, coming together, interacting to create an effect on your DV. So looking at the two variables together in a statistical analysis, when you do that, look at the two variables and their how they affect the DV together, we call that an interaction effect. Okay, so here is an example of a randomized factorial group design, or in other words, an experimental design with two IVs. Okay, so let's say that the research question is text easier to read under certain light? And then there's kind of a second research question, which is, are certain fonts easier to read under certain light? So we have type of lighting and fonts that we're looking at here. And so you would randomly assign your participants to either the incandescent light group or the fluorescent light group. And then you would go back to your 50 participants in your incandescent group, and you would randomly assign them to either read Arial font or to read Courier font. And of course, they would be doing that in that incandescent lighting. And then for the fluorescent lighting, you would go back to those 50 people and randomly assign 25 to read Arial font and 25 to read Courier font, again in that fluorescent lighting. So here your independent variable, your first one is incandescent versus fluorescent lighting or type of lighting. Independent variable 2 is type of font, so you have your two levels of that, Arial font versus Courier font. And so then what you would do is have your participants rate the readability of the text or the font that they got in the lighting condition they were in using a Likert scale, and that would constitute your dependent variable. So as a result of this, you're going to get some main effects and interaction effects. So for example, main effect A would ask the question, did the independent variable, for the first independent variable, type of light, affect the DV, in this case readability? So with main effect A, you forget about font. You're just comparing the mean score of readability for all people in the incandescent light group with all people in the fluorescent light group. And then we would also get main effect B, and this looks at did your second independent variable, which in this case is type of font, affect the DV of readability. And here you forget about the light, and you just compare the mean scores of readability for all people in the Courier font group with all people in the Arial font group. And then you would also be able to look at the interaction effect here. So is the dependent variable affected by the combination of the levels of each IV? So is the readability of Arial affected by incandescent lighting? Is Courier affected by incandescent lighting? And then you'd move to the fluorescent people. Is Arial readability affected by fluorescent lighting? Is Courier font readability affected by fluorescent lighting? So you get the scores on that using, like I said earlier, that Likert scale. I'm sure 5 would represent like very easy to read, and 1 would represent impossible to read. And so you would take all the scores for all of your groups here, and then you would run a factorial analysis of variance, or a factorial ANOVA. This one would be called a two-way factorial ANOVA because it is 2 IVs, or there are 2 IVs. If you had 3 IVs, you would call it a 3-way ANOVA. If you had 4 IVs, you'd call it a 4-way ANOVA, and so on and so forth. So I know I can do a factorial ANOVA because I have groups here that I'm looking to compare the variance between. So that's going to test a hypothesis of difference. And then I do have that interval data. and I have multiple IVs. So the appropriate statistical analysis for this type of research design would be a factorial ANOVA. And that's it for Chapter 7. Thank you for listening all the way until the end, and we will talk to you next time.